Hello everyone, how are you? So I think we are live again, right? Is my audio and video clear? Is my audio clear? On, is my audio clear? Okay, very nice then. Very nice. Chalo, so we are going to start soon. Let me just share my screen. Tell me very quickly, have you revised yesterday's class? Did you revise yesterday's class? Any doubt, any confusion, anything? No. Okay, very nice. Chalo, let us wait for 30 seconds more so that I think other people can also join. And then we are going to start very quickly. Today's lecture will be little long and a lot of derivations, a lot of, good formulas. So I am going to tell you that whatever we are going to cover today, at least one question will come in GATE 2023. Okay. So be very, attentive during the class and try to write down. Even if you are not writing down, you will get the PPTs in the recording section. So do not worry about that. Today's focus is to cover everything that we are planning to do today and have a proper revision before next class because it's very important. Okay, chalo. Very briefly, let me introduce myself. My name is Vipin Kumar, and I have done MTech from IIT Kharagpur. I've also done MSc from Politecnico di Milano, Italy, and I have around 5+ years of teaching experience. My ARS score was 675. Okay, and also you can also join me on my Telegram channel, which is the Learning Curve, for other updates. Okay, chalo. What is next? Okay. So let us start, or should you want to wait? It's already 1:02, and I am very cautious about my timing. Okay, I'm very cautious about punctuality. So, hai, it's already 3 minutes. 1:03 is it is 1:03 already. So let us start. Let us start. Okay, chalo. Now, the main two formulas that we talked about yesterday is Fourier's law of conduction, which is given by this, and Newton's law of cooling. Newton's law of convection or cooling. It is called as Newton's law of cooling. Okay, and it is the convection governing law. Okay, chalo. Now let us, so these are the important formulas that we are going to use today very, very, very frequently. Okay, chalo. Now, so yesterday we have defined the Fourier's law of conduction as Q conduction is equals to minus Ka dt by dx. So what is dt by dx? Temperature gradient in a very small element. For example, if you have a long slab, and very small element, you have this element. So what is the temperature gradient here? So this is small dx. This is small dx. Okay. And whatever temperature is varying here is gt. So it is for a very small element. This is for a small element. Now, if we want to calculate the total heat transfer in the whole slab, that means from x is equals to 0 to x is equals to L. And we want to maintain the temperature T1 at x is equals to 0 and T2 at x is equals to L. So this is our boundary conditions. What is the boundary condition? At x is equals to 0, T is equals to T1, at x is equals to L, T is equals to T2. Okay. Now, in order to calculate the total heat transfer in this slab, it is rectangular slab. Okay. So how can we calculate this? So we know for a small element, it is given by this. Now we need to integrate it around the boundary condition and we will be able to find out the total heat transfer. Okay. So we need to integrate this over the whole slab from x is equals to 0 to x is equals to L. So how can I write this? I can write Q dot conduction Tx is equals to minus Ka dt. Now we all know what is this area. This is the area perpendicular to heat transfer. So what is this area? This area. This area. If the height is h and this is width, so the area is equals to width into height. Width into height. Okay. Chalo. Now we need to integrate. So x is varying from x1 is equals to 0 to x2 is equals to 0, and temperature is varying from T1 to T2. Okay, T1 is varying from T1 to temperature is varying from T1 to T2. Okay, so Shruti have joined. Shruti, have you revised yesterday's lecture? Okay, very nice. I hope that you are not, just saying it. I hope that you have revised it because it's very important. Because you see, today only we have started with the basic Fourier's law. Okay, and today we are going to use Fourier's law, Newton's law very, very frequently. So if you have any confusion, you can ask today itself. Otherwise, this confusion will, accumulate and it will create a bigger mess. So it's not. Okay, chalo theek hai. Now we need to integrate. So this is for a small element. In order to find out the heat transfer in the whole rectangular slab, we will integrate it for the whole length. ठीक है, चलो. I'm sorry, 1 second. This is x is equals to L. This is x2 is equals to L. Okay, here x is equals to 0. Here x is equals to L. Okay, chalo. So when you do that, what will you get? Q dot conduction x2 minus x1 is equals to minus K A T2 minus T1. Okay. Now, what is this? I know that x2 is equals to L and this is 0. And also, I know that T2 is less than T1. T2 is less than T1. So what can I do? I can write plus Ka and I can swap the values of T1 minus T2. Now we will get a positive value. Okay, so here Q dot conduction is equals to Ka T1 minus T2 by L. Now this formula is valid for a rectangular slab. Rectangular slab. Area, I have already told you, area is width into height. What is length? Length is the thickness. What is L? L is the thickness of this slab. Okay, K is thermal conductivity. T1 is the temperature at one side. T2 is the temperature at other side. Okay, and the unit is watts. Unit is watts. Okay, so this is, we must know that this is thermal conductivity. Unit is watt per meter Kelvin. L is thickness of the slab. Thickness of slab. Unit is meters. A is, 1 second. I don't know what has happened. Just 1 second. Okay. And area is area perpendicular to heat transfer. And this is meter square. Okay, in this it is width into height, and T1 and T2 we all know temperature at the both sides. Okay, chalo, is it clear? This much is clear or not? Okay, chalo. Now it's because this is only one slab. This is only one slab. But what happens when there are 3 slabs adjacent to each other? When there are 2 slabs adjacent to each other, then what will happen? So it is a very good idea. It is a very convenient idea to describe our thermal circuit in terms of an electrical circuit. Okay, so we will introduce a concept of thermal resistance. How? We will make an analogy with the electrical circuit. So let's say, what is the electrical circuit? You see, if you maintain a voltage difference in an electrical circuit, so because of this voltage difference, current will flow, I, and this will be your electrical resistance. Okay, so according to Ohm's law, change in voltage is equals to I R electrical. Okay, so from here, resistance, electrical resistance is change in voltage by current. Now, what is this? This is a driving force, and this is the result of this driving force. Okay, because we have maintained the voltage different, a current is produced. Okay, a current is produced. So now, because we can make a similar analogy in a thermal circuit. So if I talk about thermal circuit, then what happens? If you maintain a temperature different in two ends, here we have T1, here we have T2, and T1 is greater than T2, so the direction of heat transfer will be like this, Q, right? Q dot, and I can say this, it is the thermal resistance. Thermal resistance. So by the same analogy, I can say that the change in temperature is equals to Q into R thermal. Okay, so R thermal is equals to delta T, change in temperature, upon the rate of heat transfer, And what is the unit? By delta T is Kelvin and Q is watt. So thermal resistance is defined in terms of Kelvin per watt. Yes, Sean, that is correct. Kelvin per watt. Very nice. I want this interaction. Shruti, also, whenever I ask a question, it's a very good idea that, like, if you know something, just write it down so that you will also revise, and I will also get a confidence that, okay, you people already know something, so that I can, go a little faster as well. Okay, chalo. Now, so if we do the analogy, so electrical circuit and thermal circuit. Now, I, which is current here, can be analogous to heat transfer. It is a driving force, voltage. It is analogous to temperature difference, and R electrical is equals to R thermal. Okay, so let us take the Fourier's law, which we have just defined. Fourier's law for a rectangular slab. So we have just defined that heat transfer due to conduction is equals to Ka T1 minus T2 by L. L is thickness. Okay. So can I write it in a way that delta T is equals to L upon Ka? Yes, I can write this, isn't it? So can I also write this as L? Can I also write this as, one second, delta T upon Q conduction is equals to L upon Ka. I can write this or not? Yes. And what is this? This is thermal resistance. So this is thermal resistance for a rectangular slab. Okay. Is it clear? Okay. Chalo. Now I can also do this for Newton's law. I can also do this for Newton's law of cooling. So what do I know? Q dot convection is equals to H A T surface minus T infinity. So can I also write this as delta T upon 1 upon HA? Yes, I can write this. So can I also write this delta T upon Q dot convection is equals to 1 upon HA? And what is this? This is thermal resistance for convection. It is for convection. Okay. Is it clear? Unit will remain same. Unit will remain same. Kelvin per resistance unit will be Kelvin per watt. Okay. So it is clear. Very nice. Chalo. Now let us take one more look over this. One more look over this. Okay. So now we all know that for a rectangular, I am talking about single rectangular slab. So what is happening? You see what is happening, that look, here we have a temperature T1, and inside the body there will be a resistance to the heat transfer that will depend on the thickness L and conductivity of this body and the area of heat transfer. Okay, and this side it's T2. So this is your R conduction. So if I draw this circuit here, T1, T2, and this is your conductive resistance, which is L upon K A, and this is the heat transfer. Okay, so I can write Q dot conduction is equals to delta T upon R of conduction, and I can say this is delta T upon L by K. Okay, is it clear? I have done nothing new. Same thing. Okay, chalo. So यहाँ पे we have got thermal resistance for conduction is equals to, up you can write it anyway. Okay, you can write it in terms of this equation, or you can write it in terms of resistance equation. Okay, so this is Kelvin per watt. Okay, now this is for a single rectangular slab. Now what will happen if we have more than one slabs and conduction and convection is happening together? So let's say there is a fluid flowing on this side. For example, air is flowing at one side. So some air is flowing this side and some air is flowing this side as well of this slab. And we have two slabs here. Okay, two slabs adjacent to each other. Now the conductivity here of this slab is K1. For this it is K2. And the thickness is L1 and L2. And this is the direction of heat transfer. Q dot is the direction. Okay. Q dot is the direction. Temperature here is T1. At the interface T2. And here it is T3. Okay. Is it clear? It's very simple. Okay. Now, the fluid that is flowing here, let's say here the heat transfer coefficient is Hi and the temperature is T infinity I. And the fluid that is flowing here, let's say this is fluid 1 and this is fluid 2. Okay. And here the heat transfer coefficient is H naught and this is T infinite naught. Okay. And the area up now you see, look, for conduction when we talk about perpendicular area. So what is perpendicular area? This is your perpendicular area. Both sides, because even it will be same in this side also. The same heat transfer area will be there. And also for convection, you see, fluid is coming from one side. So for convection also, the area will remain same. So Q dot conduction, A dot conduction is equals to A dot convection is equals to area. Okay. Conduction we take perpendicular area. Convection we take area of heat transfer. Okay, the area that is exposed to the fluid. So what area is exposed to fluid? By fluid is flowing this side. This is the fluid flowing. Okay, this is the fluid flowing. Now, what area it is flowing on? This area it is flowing. Okay, and this fluid is flowing on this area as well. Isn't it? Is it clear? Yes, very nice, very nice. So now if you would ask me to draw a thermal circuit here, how can I draw? Look, first of all, there will be a resistance of heat transfer in this fluid and at this interface. Okay, when the heat transfer will take place between the fluid and the solid body, we already know that when the fluid flows over the solid body, there is a resistance. Okay, so there will be one resistance, and the temperature difference is this side it is T infinity I, and this side it is T. Let me write it on the top. Just one second. I need some space here, so let me draw it a little. Okay, here. So one resistance is there, and this side the temperature is T infinity 1, and here it is T1. So this is your convection resistance R1. It is happening because of the fluid is transferring heat to the solid body. Then the heat will enter into the solid body. So there is an internal resistance in the solid body between temperature T1 and T2. This is your R2, conduction resistance inside the body 1. Okay. Yes, 4 resistors in series. Very nice, Sean. Very nice. Okay. Then when the heat will enter into body 2, so what will happen? There is a resistance that is between T2 and T3. Here R3. So in the body 3 also there is some resistance. And when the heat will come out, this fluid will take away some heat. So there will be some resistance, convection resistance here. Convection resistance here between T infinite out, and this is your R4. This is your R4. Is this clear? Shruti, is this clear? Okay, very nice. Very nice. Chalo. So now let us move on to what is the convection resistance. Can you tell me what is the convection resistance? Vijaya Sai has also joined. How are you? And Karthik Krishna, you also joined. How are you, Krishna and Sai? Yes, convection resistance. Okay. So here the first resistance is 1 upon Hi and A, because area is same. Fine, sir. Wherever you go, I'll follow. I see Vijaya that you are following. Very nice. Okay. Anyway, we are doing heat transfer here, so I hope you will also get a good idea of this. Okay. Chalo. Thermodynamics, so we have already done. I hope. Chalo. Let us see. Okay. And between T1 and T2, there is a conduction resistance. Can you tell me what is the conduction resistance very quickly? Between T1 and T2, what is the resistance? What is the resistance? Yes, right. L1 upon K1, and area is same. Area will remain same. Okay. I want everyone's answer, Shruti. Yes, and Vijaya also, you and Krishna as well. Everyone should participate in the class. Okay. Chalo. Now, what is the R3? What is the R3? Very quickly. Very quickly. What is R3? L2 upon K2A. Yes, very nice. And the final resistance is convection resistance H out, and area will remain same. Area will remain same. Very nice. Okay. So can I also write this in the same way that I have written Q is equals to delta T upon total resistance, I am going to take around 25 to 26 hours. I am hoping that I'll cover everything. Okay. So what is delta T? Now, because you are taking the total resistance, you have to take all the temperature difference, the whole temperature difference. Okay. So it will be T infinity I minus T infinity naught upon the total resistance. What is the total resistance? R1 plus R2 plus R3 plus R4. So this is 1 upon HIA plus L1 upon K1A plus L2 upon K2A plus 1 upon H0 A. Okay, is it clear? Okay, very nice, very nice. Okay, now you also need to understand one thing, there is this heat transfer is steady. It does not matter where it is. Okay, if even if it is happening in between this circuit or this circuit or this circuit or any circuit, the rate of heat transfer is constant. The rate of heat transfer is same. So for steady state heat transfer condition, because it is same, rate of heat transfer will remain same. Okay, so I can say Q dot is also equal to, now whatever temperature difference you are taking, you have to take their resistance. For example, let's say you are taking the first resistance only, 1 minus T1. So you will take the only resistance R1, which is equal to L 1 upon HA, which is equals to 1 upon HA. You can also take any two resistances, no problem. For example, let's say you are taking what? Let's say you are taking T infinity 1 minus T2. Two resistances you are taking. You are taking your thermal circuit from here to here. Okay. Then you have to add the R1 plus R2. So whatever temperature you are taking, so 1 upon H I A plus L1 upon Ka. Okay, so whatever temperature, you can take the last one as well, no problem. But heat transfer will remain same. Now, what temperature difference you will take to solve a problem? It depends on what they are asking in the question. Okay, we will solve few questions, you will get an idea as well. But is it clear? This much is clear or not? You tell me very quickly. No, the heat transfer is same because we are saying it is steady state. The rate of heat transfer is same. It is not changing anywhere. It is not changing anywhere. Okay, we are assuming all that we have assumed three assumptions. First is it is a steady state. The second is there is no internal heat generation. There is no internal heat generation. Heat transfer can also remain same when there is heat generation, no problem. Okay, but you have to see that how much heat is coming in, how much heat is going out. Okay, for example, if you are generating more heat but outside you have more fluid, you have high capacity fluid that is taking away more heat, then also you can have a steady state condition because the amount of heat that is generated is taken away. Okay, so it can also follow. But here we are saying because steady state condition means the temperature, this temperature difference is not changing with time. And if you are saying if you need to keep this constant, T1 you need to keep constant, then the same amount of heat is to be transferred. Similarly, if you want to keep this temperature constant, then only this heat will be transferred. Okay, so in order to keep the temperature, if you want that the temperature must not change with time, you need to transfer the same amount of heat in the whole body. Okay, chalo, is it clear? This much is clear or not? Chalo, chalo. Let's move on to one more concept. Okay, this I have already discussed. Okay, so it is not required. Okay, chalo. Overall heat transfer coefficient. What is overall heat transfer coefficient? So when both conduction and convection takes place together, when they happen together, like the case that we have just seen, then you can also use overall heat transfer coefficient, and you will see the most use of this in heat exchanger problems. Okay, how do you define this? So now we have already defined that Q dot is equals to delta T upon total resistance, which is also equal to U A delta T M. Okay, abhi we are not initially we are not going to use this equation. We will only use this in heat exchangers. Okay, but still we need to find out U, because you sometimes they ask you, okay, what is the overall heat transfer coefficient? Okay, now how can we define this? So UA is equals to 1 upon total resistance, 1 upon total resistance. This is how we can define this. Okay. If you compare these two equations, then UA is equals to 1 upon summation of R total. I can also write this as 1 upon T, like the way we have just defined, plus L1 upon K1A plus L2 upon K2A plus 1 upon H out A. 1 upon H out A is equals to UA delta Tm. So can I write UA is equals to 1 upon HIA plus L1 K1A plus L2 K2A plus 1 upon H naught A? Yes, I can write this. No, because area is same. Look, because area is same. That is why I can take out common area. Area I can take as common and area will come up here because I can take area common here. 1 upon area I can take, and I can, just 1 second, let me write this completely. Then I'll take area on the upper side. HI plus L1 K1 plus L2 K2 plus 1 upon H naught. Okay. Now because area is constant, I can write here area. And area can get cancelled. So U is equals to 1 upon HI plus L1 upon K1. You have to remember that I am taking area as constant. That's why I have cancelled the area. Sometimes it may happen that area is not constant, so you cannot take area as outside and you cannot cancel. Then you have to mind that what area you are taking. So for example, we will see later on that in cylinder, inside area and outside area are different. Okay, so whatever area you are taking in this UA, so for example in U you take inside area, then from this equation you can take inside area common and you divide everything by inside area, and then you will be able to cancel it. We will see that later on, do not worry. But here I am only able to cancel area because the area was constant. Otherwise I cannot take it as common. Do not just cancel area. You see that area is constant, then only you will be able to cancel it. Okay, is this clear? Overall heat transfer coefficient, is it clear? Okay, very nice. Chalo. Now let's see this question. Let's see. In a composite slab, we have a composite slab. The temperature at the interface, this temperature between the two material is equal to the average of the temperature of two ends. So what does this mean? It says that the interface temperature is equals to T1 plus T2 by 2, or I can also write T1 by 2 plus T2 by 2, no problem. Okay. Now assuming steady one-dimensional heat conduction. So it is steady and it is one-dimensional heat conduction. Which of the following statement is true about the respective thermal conductivity? This body has a thermal conductivity K1. This has K2. The thickness is 2B and B. Temperature here is T1. And now see, area is constant. Area is constant here. No problem. Per unit area. Okay. Area for both the blocks is constant. Is same. Okay. So can I write Q dot is equals to T1 minus T interface upon resistance 1. Okay. Let me draw thermal circuit here. So let's say this is T1, this is T inter, and this is T2. So this is R1, this is R2. What is R1? R1 is L upon Ka. What is L? 2B upon K1. Area will remain same. What is this R2? R2 is thickness, which is B, and K2A. Very quickly, if you are solving before me, just tell me what is the answer. I would really appreciate if you give me the answer before I solve this. Okay, so if you are doing it with me, then it is okay, but try to do it ahead. Try to be one step ahead than me. Okay, solve this before me. And can I also write T interface minus T2 upon R2? Yes, I can write this. Do you have any problem with this equation? Do you have any problem with this equation that I have written? Any confusion, anything? Okay, Shruti, Vijaya, is it clear? Krishna? Okay, very nice. Chalo. So I can write T1 minus T interface. R1 is how much? 2B upon K1A. And what is this? T inter minus T2 upon B upon K1, K2A. K2A. Okay. K2A. So by B and B I can cancel. Area and area I can cancel. Okay. So now how can I write this? I can write K1 T1 minus T inter is equals to 2K2. This 2 will go on the other side. This 2, yes, Sean, that is right. D is the right answer. Very nice. Shruti and Vidya, are you solving it? Please solve it before me. I'll really appreciate if you solve it before me. I'm more than happy. T inter minus T2. Okay. Now I also know that this is T1 minus T inter is what? T1 by 2 minus T2 by 2 is equals to 2K2, and this is T1 by 2 plus T2 by 2 minus T2. Okay, so if I solve this, what will I get? I'll get K1, okay, and this is how much? T1, this will be T1 by 2. Okay, I can write this as T1 minus T2 by 2 is equals to 2K2, and this is what? Here we will get minus T2 by 2, minus T2 by 2. Okay, so this is again T1 minus T2 by 2. Okay, so this will get cancelled. K1 is equals to 2K2. So this is the relationship between the thermal conductivity of these two bodies. Is it clear? So right answer is D. Shruti, Vijaya, is it clear? Okay, very nice. Vijaya, is it clear? Chalo. Let us see the next question. Now, what it is saying? Consider steady state heat conduction across the thickness in a plain composite wall. So again, we have a fluid here. There's a fluid 1. And there's a fluid 2. Same case that we have discussed. And two bodies. Okay. Now exposed to convection conditions on both sides. Now they are saying HI is equals to 20 watt per meter square Kelvin. Okay, this is HI. The H naught. H naught is also given how much? 50 watt per meter square Kelvin. Faster if we use one-dimensional steady state equation. What do you mean one-dimensional? That is what we have used, no? The same thing we have used, no? You mean that which one do you mean? That Ka dt by T1 minus T2 by L? You mean this equation? No, so it came from there only. No, it came from there. Look, the time that I have taken, you should not take this much time. You don't need, look, first of all, you don't need to write this equation. Okay, you directly write this equation. Okay, and then you can skip so many steps. So for you, it should be faster. I have to explain everything. That's why I'm taking this much time. but you can skip 1 or 2 steps in between and it will be faster for you. Everything came from there. It came from steady state only. Okay, but of course I will take more time because I cannot skip a step. I need to take all the steps to explain you. ठीक है, चलो. Okay, this question. Okay, h naught is given. Then they are saying T infinity I is equals to 20 degree, this temperature 20 degrees Celsius, this one, and outside temperature, that means this one is T infinity naught is equals to minus 2 degrees Celsius, minus 2 degree Celsius. Are you able to see me? I mean, are you able to, can you tell me, my audio is clear? Because I think I lost the connection. Okay, just 1 second, just 1 second. Just 1 second. My screen is not visible. Are you saying this? No, just 1 second. Just 1 second. I don't know. I am not getting the option of. Okay, now I am getting. Okay, now is it okay? Are you able to see this? Yes. Okay. I'm sorry. I think there was a disconnection in the internet. It got disconnected. So, chalo. Now I think it is okay. Okay, let's proceed further. Okay. So this is -2. This much is clear, or did I miss? Do I need to write this again? Do I need to write this again? Okay, chalo, ठीक है. Now they are saying K1 and K2. So this body has K1 is equals to 20 watt per meter Kelvin, and K2 is equals to 50 watt, and this L1 is 0.3 and L2 is 0.15. I'm assuming negligible contact resistance between the wall surface. You see, there is one more concept called surface resistance. So contact resistance. So in between this body, there can be some air gaps. Okay. So because of this air gaps or voids, what happens? The resistance increases. And this resistance is called as contact resistance. Between two bodies, between two interfaces, sometimes what happens? Contact resistance is because of voids filled with air. If there are voids, they can fill with air. Now air has lower thermal conductivity, so it will offer more resistances. Or there is surface roughness, so area is reduced. Surface roughness. So surface roughness, because of this, contact resistance can happen. Okay, but they are saying there is no contact resistance between the wall surface. Now they are asking, tell us the interface temperature. What is the interface temperature? Let's say it is T2, and let us assume it is T1 here and T3 here. Okay, so let me draw the circuit. We all know how to draw the circuit. Okay, first convection resistance, then conduction resistance, then one more conduction resistance, and then one more convection resistance. Okay, This is T infinite 1. Here it is T1. Here it is T2. Here it is T3. Here it is T infinite out. Okay. R1 convection resistance. R2, R3, R4. This is what 1 upon HI area. This is what L1 upon K1A. L2 upon K2A and 1 upon H0 area. Now area is same. Area is same. So can I write here Q dot is equals to the total resistance, the total temperature upon total resistance. And can I also write here, because I need to find interface temperature. Now I do not know this temperature. I do not know this temperature, so I cannot take just this. Or I do not know this temperature, so I cannot take just this. So what can I do? Either I can take these two temperatures or I can take these two. So let me take the first two. Which one? T infinite I minus T2. Because if I take only this one, no. So I have two unknowns. I do not need to know. I do not want two unknowns. I need only one unknown. So now this I know only one unknown is there. If I take T1 minus T2, although resistance will be one only, but I would have two unknowns. This is unknown, this is unknown. So I cannot do this. I need only one unknown. Okay. And I can write R1 plus R2. R1 plus R2. Okay. Is it clear till now? Tell me very quickly. Yes. Okay. So let's move on. Let me write the whole equation. So total temperature difference is how much? T infinite I minus T infinite out 1 upon HI area plus L1 upon K1 area plus L2 upon K2 area plus 1 upon H0 area. And I can write T infinite I minus T2 1 upon HIA plus L1 upon K1A. Now you need to just put all the values. I know that it is 20, I think, no? It is 20. It is how much? 20, yes. 20. So this is 20 minus 2. Now 1 upon HI. HI is how much? 20 into area. L1 is how much? L1 is 0.3 and this is 20. Okay. L1 is 0.3. This is 20 into area plus L2. L2 I know it is 0.15 and this is 50. Yes, Sean, that is correct. Very nice. It is 0.15 upon 50 into area plus 1 upon how much is H0? H0 is 50. H0 is 50 into area. Now this is, I know it is 20 minus T2 1 upon 20A plus 0.3 20A. I hope that I am not writing anything. Okay. Look. Yeah, this is 20 and K1 is also 20. Haan, to theek hai, it's correct. Okay. Now when you solve this, you will get 22 upon, you solve this and you will get some value here. Okay. And then per unit area you will get. I think this is around 0.088. And when you solve this 20 minus 22, you will get 0.065 upon area. So area and area will get cancelled. You can find out T2 is equals to 3.75. Now, what is the unit? What is the unit? It is given in degrees Celsius. And you should also know because you have put these temperature in degrees Celsius. So you will get in degrees Celsius. Okay. T2 is degrees Celsius. Is it clear? Yes, C is the correct answer, Shruti. Vijaya, have you solved this? Okay. Yes, sir. Okay. Chalo. But then give the answer, no? Give the answer before me, right? I'll be more than happy. Chalo, let's see this question. Now they are saying a weld machine steel plate of thickness L. We have a steel plate. This plate, it has thickness L. is kept such that the wall temperature are TH and TC as shown in the figure. So this is the first case. Then what happens? A smooth copper plate of the same thickness L. So a copper plate with the same thickness L is now attached to the steel plate. So now we have a steel plate, we have a copper plate. To the steel plate without any gap. So without any gap means what? Negligible contact resistance. Negligible. There is no contact resistance. Although contact resistance concept will not be asked because there is no formula that has given for this. Okay. Chalo. The temperature at the interface is Ti. Here in between the temperature is Ti, but outside the temperature is same. So here also temperature is TH and TC. Here also TH and TC. Temperature of the outer walls are still the same as TH and TC. The heat transfer rate are Q1 and Q2. Here it is Q1, here it is Q2. Okay. Per unit area. So area will remain same. So this area is same. For both the slabs, this area is same. Okay. This area and this area is same. Respectively in the direction shown. Which of the following statement is correct? So there is a relationship between TH and Q. So we have to see that what options are correct. So let us see. First I know one thing. What? Case 1. First case. So what can I write? I can write that Q1 is equals to TH minus TC upon resistance in the steel body. Right? Now case 2, can I write Q2 is equals to TH minus TC. TH minus TC. So both the resistances will come. Steel plus copper. So steel resistance. So can I say steel resistance is less than RS plus RC? Yani ki in the second case resistance is high. Can I say that? Yes or no? Any problem? Yes. Okay, very nice. So if I can say this, so that means this denominator is bigger, that means this will be smaller. So Q2 is less than Q1. Q2 is less than Q1. This is the relationship of the heat transfer. So Q2 is less than Q1. Q2 is less than Q1. Yes, that is also correct. Q1 is greater than Q2. You can also write this. Q1 is greater than Q2. Okay. Now second thing. So now we need temperature, the relationship of Ti. How can I write this? For case 2, can I write Q2 is equals to TH minus Ti, resistance in steel body, is equals to T interface minus T cold, resistance of copper body. Yes, I can write this. And this is L upon K of steel area. And this is L upon K of copper area. Now, length and length will get cancelled. Area will get cancelled because L is same they have given. And area is also same. Okay, so can I write Ks TH minus Ti is equals to Kc Ti minus Tc? Yes, now I already know thermal conductivity concept, and I know as conductivity of copper is greater than Ks. Copper ki conductivity is higher than steel. So if this, look, the product is constant. The product is same. So if Kc is higher, that means this is smaller. And if this is smaller, that means this is bigger. So I can write TH. TH minus Ti is greater than Ti minus Tc. Okay. So can I also write TH plus Tc is greater than Ti plus Ti. Okay. So I can write Ti is less than TH plus Tc by 2. Is it clear? Same concept, just little tricky question is there, but the concept is same. Shruti, Vijaya, is it clear? Okay. It needs a lot of practice. I am very, very honestly, it needs a lot of practice. You need to solve your questions yourself. Okay, it's very important. Chalo. So what is the right answer? Q1 is greater than Q2. So Q1 is greater than Q2 and Ti is less than Th plus Tc. Ti is less than, so D is the right answer. Just sorry. So the right answer is D. Very nice. Very nice. Chalo. Now let us come to the case of hollow cylinder. Now we have come to cylinder. Okay. We have come to cylinder. Now what is happening? Look, it is hollow. So in this area, this is hollow. Okay. Inside it is hollow. And this side, which is R1, at radius R1, temperature is T1. So at this radius R1, temperature is T1. And at radius R2, temperature is T2. Okay. And in cylinders, heat transfer is taking place in the radial direction. This is the radial direction, and heat transfer is taking place in the radial direction, Q dot R. Okay. Like this, it is happening. In the radial direction, heat transfer is taking place. Okay. So you can see like this. If you see the front view, this is how heat transfer is taking place. Okay. In a cylinder, in a hollow cylinder. Now, what is the boundary condition? At R is equals to inner radius R1, temperature is equals to T1. At R is equals to R2, T is equals to T2. T is equals to T2. So we will start again from Fourier's law. Fourier's law of conduction. What is this? It is Q dot conduction is equals to minus Ka dt by dx. Dx होगा? Is it dx or something else? dr. Very nice. Because the heat transfer is happening in the radial direction, in the direction of radius. So it is always in the direction of heat transfer, dr. Okay. Only in one direction. You see there are three directions. One is this direction. Okay. One is this direction, radial direction, and one is again this direction. Okay. But in the other direction, because the length is really long, so the heat transfer is insignificant. The heat transfer is only significant in the radial direction. Okay. So that is why we are assuming that it is only one dimensional heat transfer, which is in radial direction, Okay. Now what is the area? What is the area of this? 2 pi RL. Cylindrical surface area is what? 2 pi RL. 2 pi RL. Okay. So can I write this Q dot conduction minus K 2 pi RL dt by dr? Again, we are doing the same thing what we did for the rectangular body. Dr by R is equals to minus K 2 pi L dt. So this equation is only valid for a small radius. Okay, you see here, you take a small radius here, dr, very small radius. This is your dr. So it is only valid for a small element, But in order to find out in the total thickness, then we need to integrate this. Okay, so we will integrate this from R1 to R2, and this is T1 to T2. So when you integrate this, you will get Q dot conduction ln R, and this is R1 by R2 is equals to minus K 2 pi L T2 minus T1, T2 minus T1. Okay, so can I write this as Q dot conduction ln R2 by R1 is equals to let me write it plus K. Okay, plus K. In fact, I'll write in the form that is very widely used. I'll write this as 2 pi K. I'll bring K here L. Now because plus I have taken, so I'll swap the values of temperature. Okay. Yes. 2 pi k L T1 minus T2 ln R2 minus R1. Sean is correct. Very nice. Very nice. I would really appreciate this. Now I can write this in the form 2 pi k L T1 minus T2 upon ln R2 by R1. R2 by R1. So this is the heat transfer equation. This is the heat transfer equation for cylindrical body. If there is a single hollow cylinder, so I can calculate heat transfer in R direction, conduction heat transfer. How? 2 pi k L. What is L? L is the length of the cylindrical body, the length of the cylindrical body. K is the thermal conductivity. T1 is the inside temperature, T2 is the outside temperature, and L ln R2 by R1. Okay, so R1 is inner radius, R2 is outer radius, T1 is temperature at inner radius, Ri, T2 is temperature at outer radius, L is length of cylinder, K is thermal conductivity of the body, thermal conductivity. Okay, now the unit is watts. The unit is watts. Now tell me, can I? So this is one of the important equation that you will be using frequently. Now let us move on. Can I also write this as Q dot R conduction is equals to T1 minus T2 upon ln R2 by R1 2 pi KL. Yes. And can I write this as delta T upon thermal resistance in cylinder? Yes. Okay. Is it clear? Is it clear? In the same form I have written. Shruti and Vijaya, is it clear? Okay. So now what do I get from here? That the thermal resistance in a cylinder, I can write ln R2 by R1 2 pi KL. Very important that we can, it is only valid for a hollow cylinder. It is valid for a hollow cylinder. Hollow cylinder. Okay. Clear? And unit will be what? Kelvin per watt. Any confusion here? I'm just waiting because I think someone is typing. So let me see if you have any confusion, then we'll move on. Yes, and you got so many questions also from 2022. Yesterday I showed you got 8 marks of heat and mass transfer, which is very unusual. Okay, which is very unusual. So yes, I mean it was lengthy, so were there, but let's hope it will not be the case for 2023. Okay, usually you get, look, even in heat and mass transfer, in heat transfer there were long questions, but there were few questions that were easy. Okay, so if you just try it once, if you think it is going to take more time, then it is not worth it in gate. So leave that question and move ahead. Come back to the question in the end if you have time. Otherwise, solve the questions that you can solve in one go. Okay, chalo. So this much is clear, then we can move on. Okay, Shruti and Vijaya, can we move on? Already 1 hour is done and we have to cover a lot of things. Okay, so I have told you today's class will be longer. Chalo. Now this is a composite cylinder where we have more than one cylinder, and also there is a fluid here. There is fluid inside this, and outside also there is fluid too. So let us say that the heat transfer coefficient is There is a inside fluid, like hot fluid is there, inside hot fluid is there, and it is Hi, and the temperature of fluid is T infinite I. Outside fluid is also there. Heat transfer coefficient is H naught, and temperature is T infinite naught. And at R1, at radius R1, temperature is T1. At radius R2, temperature is T2. At radius R3, temperature is T3. Now these body have some thermal conductivity as well because it is solid body. Okay, so let's say it has K1, it has K2. Okay, so if again now I have to draw the thermal circuit here. I have to draw the thermal circuit here. Okay, how can I draw the thermal circuit? So I can draw the thermal circuit like this. First of all, there will be some resistance between the fluid and this solid body when the heat transfer will enter into the first cylinder. Then there will be a resistance here. So this is T infinite 1 and this is T1. Okay, let me choose black color because this is looks very bright. Okay, so look, first of all, when heat will enter in this body, there will be some convection resistance. Then there will be some conduction resistance inside this body body first cylinder or inner cylinder. Then outer cylinder will have some resistance and then convection resistance here. Okay, so the temperature here is T infinite I. Here it is T1. Here it is T2. Here it is T3. And it is T infinite out. And this is R1. This is R2, R3, and R4. So can I draw this here? Let me draw this here. Okay, so we have T infinite I and T1, convection resistance R1. Then we have T2, we have T3, and we have T infinite out. Here we have R2, R3, R4. Four resistances are there. Four resistances are there. Now, what is the resistance R1? Convection resistance Hi, and area. Area is how much? 2 pi Ri inside L. Inside radius will take. Okay. Then what is R2? R2 is conduction resistance. What is conduction resistance? Ln R2 by R1 2 pi K1 L. L is same. Length of the cylinder will remain same. No worries. Then what is the outer radius resistance? Outer cylinder resistance? R3 by R2 2 pi K2. K2 this one L. And then I'll take what? 1 upon H out 2 pi. Now radius will be outside R3. R3 L. Is it clear? Is this much clear? Tell me very quickly. Okay. Okay. Chalo. So now can I write if I need to calculate Q dot conduction in the cylinder, can I write T infinite I minus T infinite naught upon sum of total resistance, and this will be equal to R1 plus R2 plus R3 plus R4. I can write like this. And in order for steady state, I don't have a steady state heat conduction. So the rate of heat transfer is same. Rate of heat transfer will remain same. So I can take any two resistances or one resistances. For example, I can take the first resistance and I can take R1. Or I can take any two. For example, I can take T2 to T infinity. So T2 minus T infinity naught. So I will take R3 plus R4. No problem. Any problem with this? Is it clear? Okay, very nice. Very nice, very nice. So let us move on. Let us move on to the problem. Okay, so it is we have already discussed this, so I don't need this space. Let us move on to the question. Now, GATE 2007 2 marks question. You see how easy this question is, and it is of 2 marks. Okay, a long glass cylinder of inner dia. Inner dia is how much? 0.03. So inner radius is how much? 0.015 meter. Okay, inner radius is 0.015 meter. Outer dia is this much. Outer dia is, so I can write 0.025 meter. 0.025 meter. Carries hot fluid inside. If the thermal conductivity of glass, so it has a glass. Okay, so it has a thermal conductivity of 1.05. So K is equals to 1.05. The thermal resistance per unit length of the cylinder. Thermal resistance I need to find out. Per unit length of cylinder. We all know thermal resistance in a cylinder, in a solid body. Look, they have not given us H. They are saying there is a hot fluid inside, but they have given no information about what is H. What is H? So that means they do not want to calculate us. They do not want us to calculate take the internal resistance. Only in the solid body I need. Yes, Sean, that is correct. Okay, that is very, very nice. Shruti, also you will try. Vijaya, please try to solve it before me. Look, I need to take time. I need to write the values. I need to explain everything. But I hope that you reach a level that you finish the question like this type of question in 30 seconds. I want this kind of level of preparation from you people. Okay, chalo. So I can write ln r2 by r1 and 2 pi kl. We already know this. And everything we know. ln, and they are asking per unit length. Per unit length means length will be 1 meter. Okay, now r2 is 0.025 and this is 0.015. 2 pi k is 1.05 into 1. So if you solve this, 0.077 in Kelvin per watt. Very nice, very nice. This is your thermal resistance in cylinder. Okay, this is the right answer. B is the right answer. Okay, is it clear? Shruti? Okay, yes, Vijay, B is the correct answer. Very nice. Chalo, let us move on to the next question. A stainless steel tube whose stainless steel tube is there, KS is this. So there is a steel tube. There is a steel tube whose conductivity is 19 watt per meter Kelvin and 2 centimeter inner dia. Okay, so that means R1 is equals to 2 centimeter. So R1 is 1 centimeter, or I can say 0.01 meter. 0.01 meter. Okay. Now, the outer dia is 5. So R2 is equals to 2.5 centimeter. So it is 0.025 meter. Is insulated. Now this steel tube is insulated with 3 centimeter thick asbestos. So this is an insulation. Okay. And the thickness is 3 centimeter. So what can I write? R3 is equals to 2.5 plus 3 means 5.5 centimeter. So 0.055 meter. Okay. And the conductivity of this asbestos layer is 0.2 watt per meter Kelvin. If the temperature difference between the innermost and outermost surface is 600 degrees Celsius. Okay. So what is the innermost? If this T1, this is T2, this is T3. So they are saying T1 minus T3 is equals to 600 degrees Celsius. The heat transfer per unit length, I need to calculate. Okay, how will I do that? Q dot in cylinder, I know I can write T1 minus T3 upon R1 plus R2. Okay, so this is T1 minus T3 ln R2 by R1 2 pi Ks L, okay, plus ln R3 by R1 2 pi Ka L. Now they are saying heat transfer rate per unit length. So either you can take length is equals to 1, or you can take length common here and take in the numerator, and then from the numerator you can bring it here. You can bring it like this, or you can cylinder by length is equals to 600 by ln. R2 is how much? 0.025 upon 0.01 upon 2 pi. K is 19 plus length I have already taken and written on the other side. R3 is how much? 0.055 upon 0.025. This is R3 by R2, not R3 by R2, okay, not R1. 2 pi, and this is 0.2, okay. And already, yes, Vijaya, that is correct. Very nice. So Vijaya has solved this. You will get 944.7 watt per meter. Watt per meter. Watt per meter. Very nice. Shruti, have you solved this? Sean, have you solved this? Are you getting the right answer? Yes. Okay. Very nice. If you are getting the same answer, just 1 second. Let me drink some water. Okay. So we have still enough time. Very nice. Now, so the answer is C. Okay. Chalo. Solve this question very quickly. It's a little, okay. Let me explain this. Now, what is happening? Look, we have a cylindrical uranium fuel rod of radius. We have a fuel rod, uranium, that means nuclear rod. Okay. And the radius is 5 millimeter. And because it is a nuclear rod, there will be nuclear chemical reactions going on inside the tube, inside the rod, and it will be generating some heat. There will be heat generation. So Q dot generation is how much? 4 watt per meter cube. Okay. Now the rod is cooled by a liquid at 25 degrees Celsius. So there is a fluid that is surrounding the rod. Okay. It is dipped in a fluid. It is dipped in a fluid in a tank or somewhere. So this temperature is of this fluid is 25 degrees Celsius, and heat transfer coefficient is 1000 watt per meter square. At steady state, the surface temperature of the rod. We need to find out the surface temperature of the rod at steady state. Now you tell me, in order to satisfy steady state condition. Steady state means what? The temperature of this surface will not change with respect to time. It will not change. So what? How can you maintain that? How can you maintain the same temperature? It will not be affected at any time. If you see after 1 minute, after 10 minutes, after 15 minutes, it will remain same. The only condition it will happen when whatever heat is generated will be taken away by the fluid. Because if the fluid is taking less heat, that means the temperature will increase. If the fluid is taking more heat, that means the temperature will decrease. So if Q dot generation is equals to Q dot convection, then only you can satisfy steady state. Is it clear? Is it clear? Whatever heat is generated, that heat will be taken away by the fluid. Only then the temperature will remain constant. Okay? Vijay, is it clear? Shruti, is it clear? Chalo. Very nice, very nice. Chalo, so what is Q generation? It is 4 into 10 to the power 7 watt per meter cube is equals to Q dot convection. I know HA T surface minus T infinity. Now this is in watt per meter cube. This is in watt. And so I cannot solve this. I need to multiply it by volume. Then only I will be able to make uniformity of the equation. Okay. So now it is watt. Okay. So what can I write? 4 into 10 to the power 7 into pi by 4. Let me write this in radius terms. Okay. Pi r square L is equals to h 2 pi r L Ts minus T infinity. Now I know everything. What do I know? 10 to the power 7. Radius is how much? 5 millimeters, 0.005 square into, in fact, what can I do? I can cancel this. Radius and radius will get cancelled. Pi and pi will get cancelled. R and R will get cancelled. So I don't need this. And I can write is equals to H is 1000 watt per meter Kelvin, and 2 Ts I need to calculate. T infinity is 25. So if you put this in 25, the answer you will get in, if you put this in degree Celsius, answer you will get in degree Celsius. If you put this in Kelvin, for example, if I put this 298, because 25 degrees Celsius is 298. Now I can directly get the answer in Kelvin, which Vijaya has solved 398 Kelvin. It is correct. 398 Kelvin is correct. Is it clear, Shruti and Sean? Chalo, very nice. Very nice. Shruti, are you still solving this? Okay, so is it clear? Chalo, let us move on. Now there is a concept called critical radius of insulation. It is also called as critical thickness of insulation sometimes. Okay. Now, what does it mean? It means the thickness or the radius at which heat transfer is maximum. The radius at which heat transfer is maximum is called as critical thickness. Okay. Now, why do we need this concept? So you see, like for example, your electrical wires are there. You see electrical wires are there and they are wrapped with insulations. Why they are wrapped with insulations? There is a rubber covering over that, right? And rubber has very low thermal conductivity, so it's kind of insulation. So why do you need to insulate them? Look, insulation does not mean that it is going to reduce the heat transfer. Okay, it means that you are covering something. Now there is current flowing. You know, there are wires and there is current flowing inside this I. Because of this current, there is some resistances. Because of this resistances, heat transfer will take place in the wires for best thickness to maximize heat transfer. Yes. Yeah, but why do we need to maximize heat transfer? That is what I am trying to explain. Okay. Why do we try to maximize the heat transfer? So, one second. Yeah. So, for example, you have a wire and current is flowing. Okay. Now, because of current, there will be resistances. Because of resistances, there will be heat generated. Okay. So, the temperature of the wire is going to increase. Now, as the temperature is going to increase, there will be more resistance and more loss of power. Okay. So now, in order to increase, so that whatever heat is generated, you cannot do anything about the heat. If you are passing current, then heat will be generated because resistance will be there. But what can you do? You can conduct that heat out. So what do? We insulate this by insulation. Okay. Now, based on the thickness of the insulation R, the heat transfer may increase or may decrease. But when you increase R, the heat transfer increases and it becomes maximum at a certain radius. After that, it starts decreasing. So the point, the radius at which it is maximum is called as critical radius of insulation. Okay, at that insulation thickness or at that insulation radius, heat transfer will be maximum. So the temperature of the wire will be minimum. So the losses will be minimum. Okay, is it clear? Why do we need to maximize the heat transfer? And there are other applications as well. This is one of the applications. There are other applications as well. Okay, because you see in chemical reactions in a nuclear rod also, you need to maintain a constant temperature. If you increase the temperature, it basically degrades the performance of the chemical reactions. The chemical reactions takes place at a particular temperature. If you are not removing heat and the temperature is going up, then it is going to negatively affect your chemical reactions. So what do you need? You need to maintain a constant temperature. So you need to maximize the amount of heat transfer. Okay. The radius at which heat transfer is maximum is called as critical radius of insulation. It is also referred as critical thickness of insulation. It depends on thermal conductivity of insulation K and external convective resistance heat transfer coefficient H. Okay. Now, how do you get this? How do you get this? You see, look, you have this wire. You have this wire. This is the wire. Now, this is the insulation that you have provided. The insulation you have provided. Now, the radius of wire. I think my video is again gone, right? If I am not wrong. My video is gone, no? Okay, it's fine. Okay, ठीक है. Some internet connectivity problem is there. Anyway, so I hope it is there. Okay, audio and video both are, audio and screen both are visible, right? Okay, chalo, ठीक है. Okay, so let's say this is the wire and the radius of wire is R1. This is the wire and the radius of wire is R1. Now you are adding insulation and you want to know at what radius R the heat transfer will be maximum. So how can you do that? Look, let's say here it is T1 and outside the fluid, the air that is there has temperature. Yes, derivate with respect to R and equate to 0. Very nice. Yes. So what do we do? Ti minus T0 upon ln R, outer R by R1 upon. Now this R is variable. You can change this R. Okay, I'm not writing R2. I can change this R. 2 pi K of this insulation. Okay, K insulation into L plus 1 upon H0 of the air that is outside into area 2 pi RL. Okay, is this clear? Is there any confusion in this? Okay, now let's see. Now this is your conduction resistance. This is your conduction resistance happening inside the wire. This is your convection resistance, R convection. Now when you are increasing this R, when you are increasing the radius, outer radius, when you are increasing, so you see this is increasing. So R conduction is increasing. And R convection is decreasing. I don't know what has happened. Just wait. Are you able to? Just 1 second. Let me check here. Is my screen clear? Because I think I again lost the connectivity. I have opened actually it in another laptop as well. So that laptop is, having bad internet connectivity. So I don't know if it is just for my another laptop or for you as well. But anyway, so I just stop every time it happens in my another laptop. Chalo. Let me check its internet connectivity. How it is connected. Okay, okay, ठीक है, चलो चलो. Is it clear, right? This much is clear or not? As you are increasing R, so you see R is in numerator here. R is in numerator here, so conduction resistance is going to increase, and this is in denominator, so R convection is reducing. Okay, is this clear? This much is clear or not? Okay, 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 okay. So now what actually happens is, look, when you increase this R, the increase in conduction resistance, and there's a decrease in convection resistance. Now the combination of this will tell you that R total is increasing or it is decreasing, based upon which quantity is increasing more and which quantity is decreasing more. Okay, so based on that I can find out that if my R total resistance, this total resistance is increasing or decreasing. Okay, so to find out the value of R at which R total is maximum or minimum, what can I do? I can, so this is my R total, right? This is my R total. R total is what? ln R by R1 upon 2 pi KL plus 1 upon R naught 2 pi RL. So what can I do? I can differentiate R total with respect to R. And I can put this equals to 0. Now derivation I am not doing, because for gate it is not required. There is no point in doing the derivation. I mean, if we are, at a certain initial point, for example, if we are preparing in July, August, then I can do this derivation as well, no problem. But right now, anyway, we have sort of time. So derivation is anyway not required. Okay. Now, when you do this in differentiation and put that equal to 0, then what will you find? That R ki value you can find here. R is equals to K of insulation upon outside heat transfer coefficient. At this value, you will get either a maximum or a minimum. And when we differentiate it again one more time, and we put the value of R, then we see that this is R total is minimum at this radius. And if R total is minimum, if that means the denominator is minimum, that means the heat transfer Q dot is maximum. At this radius. So is it clear? So I can say that at R is equals to K insulation upon outside this, R total is minimum and heat transfer Q is maximum. And this is called as critical radius of insulation, and this formula is valid for a hollow cylinder. Okay, is it clear, everyone? Shruti, Vijaya, is it clear? Chalo. So let us see one more thing, the graph of this radius. Okay, so what is happening? Look, I know that R total is equals to ln R by R1 by 2 pi KL plus 1 upon H naught 2 pi RL. Okay, so this is your conduction resistance. This is your convection resistance. Now, when your radius, like you are increasing the radius, okay, you are increasing the outer radius, you are increasing this R, okay, but your R is still less than the critical radius. So what will happen? R conduction, you are increasing R conduction. So what will happen? Resistance due to conduction is going to increase, yes, but the decrease of resistance due to convection is more. is more. So therefore, R total is going to decrease and heat transfer is going to increase. So you see, when your R is less than RC, so your heat transfer is increasing. It is increasing. Okay. Now at R is equals to RC, heat R total is minimum and heat transfer is maximum. Heat transfer is maximum. Okay, heat transfer is maximum. Then when R is greater than RC, so after this point, what happens? The increase in resistance conduction is more than the decrease in convection resistance. So what happens? R total is increasing and heat transfer starts decreasing. So now heat transfer starts decreasing and therefore there is a decrease in heat transfer and the wire can get hot and hot and hot. Okay, is it clear? So the resistance is RK upon H0 for cylinder. Yes. Clear? Shruti, is it clear? So let us see this question. With an increase in the thickness of insulation, if you are increasing the thickness of insulation around a circular pipe, heat loss to surrounding due to heat loss to the surrounding due to. What is the right answer? Tell me very quickly. What is the right answer? You see, if R is less than RC, conduction resistance is increasing and convection resistance is decreasing. So Q dot conduction, heat transfer due to conduction is decreasing, heat transfer due to convection is increasing. Okay, so what is the right answer? Heat loss to surrounding due to what? What is the right answer? Very quickly tell me. A is the right answer. Yes. Shruti, are you able to understand this? Is it clear? Vijaya, is it clear? Why A? Because if resistance is less than RC, convection resistance is decreasing. So heat transfer due to convection is more than the heat transfer in conduction. Conduction is decreasing. Okay. So heat loss that is happening because of convection is increasing while due to conduction is decreasing. Okay. Is it clear? I have just told you. Okay. This thing. Shruti, is it clear? Vijaya. Okay, Vijaya went offline. Chalo, theek hai. She'll come anyway. Okay, chalo. Let's move on. Chalo. Next question. Gate 2000, 1 mark question. I don't think I need to tell you anything. Read the question very quickly and answer what is the right and tell me what is the right answer. I don't think I need to tell you anything about this. Okay. The answer is 12.5. Very nice. Very nice. Yes. RC is by K insulation upon H naught. Okay. 8, 1 by 8. I'm sorry, just 1 second. 1 by 8. Okay. So you will get how much? 0.125 meter or 12.5 centimeter. Okay, very nice. Chalo, let us move on to the next question. Very simple question. You see this one question as well. A pipe of 25 millimeter outer diameter. So the outer diameter is how much? Outer diameter is 25 millimeter, which is 0.0. Let us write 25 only. Let us write 25. The heat transfer coefficient between the cylinder and the surrounding is 5. H is equals to 5 watt per meter square Kelvin. Now it is proposed to reduce the heat loss. You want to reduce the heat loss from the pipe by adding insulation having a thermal conductivity of 0.05. So insulation material thermal conductivity is 0.05. Now which one of the following statement is true? Okay. So what we need to find out, ki if R is greater than R naught, if critical radius is greater than R naught, then in fact let us write if it is less, then heat transfer will increase. If it is equal to RC, then heat transfer is maximum, and if critical radius is greater than R naught, then heat transfer is going to decrease. So let us find out first RC. Let us find out RC first. So RC is equals to how much? K insulation upon H naught. 0.05 upon 5. Okay. And this is 0.01 meter, which is 10 millimeter. Okay. And how much radius? Radius is 12.5, not 25. Diameter is 25. 12.5 millimeter. So I can say that this is less than outer radius because this is 10 and this is already 12.5. Okay. So by critical radius is less than RC. So if you are adding into, so adding the insulation will reduce the heat loss. Okay. It is already at R naught. It is already at R naught. So now if you increase the thickness, if you are, look, this is already 12.5. Now if you are adding insulation, then what will happen? You will be working on this side of curve. Okay, because you are already on this side. Yes, option C is correct. Okay, so because your R critical radius is less than R naught, so you are already here. If you will add insulation, your heat transfer will reduce. Is it clear? Is it clear? Shruti, Vijaya, is it clear? Then we will move on very quickly. So adding the insulation will reduce the heat transfer. First option is saying what? The outer radius of pipe is equal to critical radius. No, it is not equal. The outer radius of the pipe is less than critical radius. No, it is greater. Outer radius is greater. So second is also not correct. Now adding the insulation will reduce the heat loss. Yes, it will reduce the heat loss. Adding the insulation will increase the heat loss. No, it will increase the heat loss when critical radius is greater than R naught. When critical radius is, no, when, one second. When RC, when R naught is less than RC. Okay, then if you add the insulation, you increase the RC, then the when you add the insulation, radius will increase and the heat transfer will increase. Okay, is it clear? Okay, Shruti and Vijaya, is it clear? Okay, chalo. It will, of course, it will need more practice, more and more practice. Only then you will be able to do this. Okay. Abhi, even if there are some doubts, you can, of course, you can ask me, but I would tell you that you solve more and more and more questions, then you will get more clarity, because there are so many formulas. And also do one more thing: whatever formulas that we are covering today, make a short notes of them. Write it separately on write it on a separate piece of paper, and then revise them. Okay, because there are so many formulas, and of course you will get confused. What is the resistance for a rectangular slab? What is the resistance for a cylinder, for a sphere? What is the heat transfer equation? What is critical radius? So please write it down on a separate piece of paper. It's very important. Today we have covered so many formulas, and still so many formulas are left. Okay, and today maybe we can continue till 350 or 320 or 330. I think we will see. Let's try to cover everything in time. But even if we need to extend 15-20 minutes, I hope that you are okay, because I already told you yesterday that today's class will be longer. Okay, chalo. Now let us go to single hollow sphere. The same concept that we applied for a cylinder. Okay, now the heat transfer is again in the radial direction. Inside radius is R1, temperature here is T1, and outside radius is R2, temperature here is T2. So what is the boundary condition? At R is equals to R1, T is equals to T1, at R is equals to R2, T is equals to T2. Now for analysis, let me take a small dr here. Okay, at a radius R, I am taking a small dr. Okay, so what is the heat transfer through this small dr? What is the Q dot conduction in a sphere? Fourier's law, minus Ka dt by dr. Okay, now in order to find, it is for a small element, now to find out the for heat transfer for the whole thickness. Okay, what do I need to do? I need to, and what is A? A is equals to, what is A? 4 pi r square. Okay, so Q dot conduction is equals to minus K 4 pi r square dt by dr. So I can write the same way. What? Dr by r square is equals to minus K 4 pi dt. Okay, so I have to integrate it from R1 to R2, from T1 to T2. So Q dot conduction 1 upon R, R1 by R2, 1 minus 4 pi T2 minus T1. Okay, so what can I write here? Q dot conduction 1 upon R2. It is minus 1 upon R. So it will be 1 upon R1 minus R2. Okay. Is equals to, now I will take plus 4 pi K and I'll swap the temperature values. Okay. So Q dot conduction, can I write 4 pi K T1 minus T2 1 upon R1 1 upon R2, or it can also be written as R1 into R2 T1 minus T2 R2 minus R1. This is the most frequently used equation. So let me summarize here. So what did we find out? Q dot R in sphere is equals to 4 pi K inner radius, outer radius, T1 minus T2, R2 minus R1. Very frequently you will use this equation. The unit is watts. Okay, is this clear? Yes, that is also. I'm just going to talk about this. Shruti and okay, Vijay, is it clear? Chalo. Now, this is heat transfer. Now, I also know, what can I write? Can I write like this? T1 minus T2 upon R2 minus R1 4 pi K R1 into R2. Can I write it like this? R thermal of sphere. Yes, I can write this. So of course, what can I write? Thermal resistance for a sphere is R2 minus R1 4 pi K R1 R2, and the unit is Kelvin per watt. Kelvin per watt. Okay, because it is delta T by Q. Okay, is it clear? Chalo. So now same concept we are going to apply for the composite hollow sphere like we did earlier. So I don't think I need to explain a lot of things here. There is a fluid here with conductivity Hi and temperature T infinity I. Outside fluid is there H naught, T infinite out, and it is already at T1, T2, and T3. So can I draw a thermal circuit? So it is T infinite I, this is T1, this is T2, this is T3, and this is T infinite out. Okay, now here we have convection resistance 1, conduction resistance 2, conduction resistance 3, and outer convection resistance. Okay, now what are the values? By here, so it will remain same. H inside and area. H inside and area. What is the area? What is the area? 4 pi Ri square. Okay. Now R2 is the conduction resistance inside the first body, first sphere and second sphere. It has K1, it has K2. Okay. So R2 minus R1, 4 pi K1, R1, R2. What is R3? R3 by R2, 4 pi K, R3, R2. And what is the final one? 1 upon H outside, 4 pi R outside, which is R3 square. Is it clear? Shruti, I am waiting for you, and Vijaya. Is it clear? Everyone should write. Okay, don't wait for me that I call your name. Whenever I say, is it clear? So if you have any doubt, just write it down. Otherwise, say yes, sir. Okay, so that we can move on very quickly. Don't wait for me, I'll take your name. Okay, chalo, let us move on. Now, so I know everything here. How can I calculate heat transfer by sphere? Is equals to T infinite I minus T infinite out summation of total resistance. Okay, and I can say minus T infinite out R1 plus R2 plus R3 plus R4. Okay, and to satisfy the steady state condition, I can also say I can take any one temperature difference, whatever I want. What do you want? Let's say T infinite minus T3 le lo. You can take T3. So what will you do? R1 plus R2 plus R3. Or you can take any two like T2 minus T3. T2 minus T3, so you can take R3. Whatever you want to take, you take. No problem. Okay, is it clear? Now, so we are repeating the same thing. So it must be clear. You know? Is it clear? Chalo, let us move on. Let us also understand so this is the same thing. Now we do not need more space for it because we have already explained. Critical radius of insulation for hollow sphere. So what do we know? By Q of sphere is equals to, so let's say this is R1, this is sphere, this is sphere. Okay, so can I say here it is T1, Outside the temperature is T naught. Outside the temperature is T naught. So can I say T1 minus T infinity? This is T infinity. Okay. And first of all, conduction resistance will be there and then convection resistance. So T1 minus T infinity. What is the conduction resistance? R, not R2. Let us take R because we are going to vary the R. R minus R1 4 pi K R into R1 minus plus 1 upon outside H 4 pi outside R square, small r bus. Okay. Now we can say that if you are increasing R, this can increase or decrease. Also, it is decreasing. Okay. This is conduction. It may increase, it may decrease because R is here as well. R convection is decreasing. Okay. Based on them, the total value of resistance will either increase or decrease. And similarly, based on that, Q dot will increase or decrease. 1 second, ये मैंने उल्टा, this is it. So based on this, Q, if it is increasing, so it will decrease. If it is decreasing, the heat transfer will increase. Now, to find value of R at which R total is maximum or minimum. So what will we do? R total by del R. What is your R total? This is your R total. Okay. This is your R total. This is your R total. Okay. So you differentiate it and you put it is equals to 0. Okay. And when you do this, you will get the value of R as 2K of insulation upon H naught. And again, when you do double differentiation and put the value of R, what will you get? That R total is, now this is the value of R where R total can be maximum or minimum. So how do I find out it is maximum or minimum? I'll differentiate it one more time, put the value of R. Okay. So I can find out that at this R total is minimum and heat transfer is maximum. So can I say that at this radius, critical radius, 2K of insulation upon outside heat transfer coefficient, R total is minimum and heat transfer is maximum. So this is your critical radius of insulation for a sphere. Okay, is it clear? Chalo. Let us move on. Up there are some small topics. So main part we have covered. Now there are some small topics that we will very quickly cover in next 15-20 minutes. Okay. Now look, the resistance that we know, it can be any connections. For example, two slabs are arranged in series or they can be arranged in parallel as well. For example, if Q is going like this, so what will be the thermal circuit? Look, this will be your thermal circuit. Let me change the color. This is T1, this is T2, this is T3. Okay, so thermal circuit will be like this. T1, T2, T3, R1, R2. So in order to find R total, if it is arranged in series, so this is the series arrangement. Okay, so R total can be calculated as R1 plus R2. Now R1, now it is a rectangular slab. Now it could be a cylinder. It could be a sphere. Now based on that, we can take the value of R1 and R2. Okay? So if it is series connection, you can calculate R total like this. Okay, that we are already doing for some time, that we have already seen. Okay, is it clear? Okay, now if it is in parallel, for example, this is the direction of heat transfer. What is your thermal circuit? Thermal circuit will be like something like this. Now R1, R2, R3. Okay, so this is the parallel connection. This is the parallel connection. Now, how do you calculate? How do you calculate? So 1 upon R equivalent is equals to 1 upon R1 plus 1 upon R2 plus 1 upon R3. That is how you can calculate for parallel connections. Same thing, what we know from electrical circuit, we will apply here. Okay. Now there could be a combined arrangement. For example, this is the Q. So heat transfer will take place like this, and then it is okay. T1, T2, T3. Okay. This is, let's say, R1. Let's say this is R2. Let's say this is R3. Okay. So how do you calculate total resistance? Total resistance will be equal to R1 plus R equivalent. R equivalent. Now I need to calculate R equivalent. So 1 upon R equivalent is equals to 1 upon R2 plus 1 upon R3. So R equivalent you can write as what? R2 into R3 by R2 plus R3. Okay, if you solve this, R equivalent is equals to R2 into R3, because it will be in the denominator, okay? And in numerator it will be R2 plus R3. But when you take 1 upon R equivalent, you can find this. Is it clear? Is it clear? Chalo. If it is clear, let's very quickly solve one question. This is the question of GATE 2005, 2 marks question. 2 marks question. Okay. Same thing what we have done till now. This is thermal resistance. Then this is thermal resistance. This is thermal resistance. And this. Okay. Overall thermal resistance I need to find out. Overall. Okay. So this is, let's say, R1, R2, R3, Q, Q, Q. Okay. So what is overall thermal resistance? Bhaiya, overall yani ki total is equals to R1 plus R equivalent. And what is R equivalent? R2 into R3 upon R2 plus R3. Okay. So let me find out. What is R1? R1, how can I calculate R1? R1 is equals to L1 upon K1 area. Okay. And the depth they are saying 1 meter. Yani ki height and depth is 1 meter. So area is 1 into 1. Okay. So L1 is how much? 0.5. K is 0.02. And area is 1 into 1. So calculate how much is it. Tell me. Then it is L2 upon K2 area. L2 is how much? L2 is 0.25. K2 is 0. This is K2. This is K3. This is K1. K2, K3. Okay. So K2 is 0.1 and it is area is 0.5 into 1. Very quickly solve this and tell me what is R2. Then R3. R3 is equals to L3 upon K3 area. L3 is same. K3 is 0.04 into area is this. Now tell me very quickly how much is R2 and R3. R1, R2, R3. Tell me, yaar, very quickly. Then calculate R equivalent. R2 into R3 upon R2 plus R3. Sean, how much is your, tell me, how much is R2? R1, R2, R3? R2 is 0.8. Is it correct? It doesn't seem to be correct, yeah. 0.25 divided by 0.1 into 0.5. It is 5, no? It is 5. Why? How are you saying 0.8? I have just calculated in my calculator. Yes, R2 is 5. What is R1? What is R1? Sean, how you are getting R2 wrong? This is 25. That is correct, Shruti. What is R3? R3. Yes, 12.5. So what is R equivalent? What is R equivalent? How much is this? Acha, L and K got changed. That is why practice is required. Sean, that is the reason that practice is required. Okay. Chalo. R equivalent. Shruti, how much is R equivalent? Vijaya, R equivalent. R2 into R3 upon R2 plus R3. Yes, C is the correct answer. Yes. So this you will get 3.57 and this is already 25 plus 3.57. So the answer is 28.6. That is correct. Very nice. Sean, you have lagged behind. Okay. Shruti has left you behind. Okay. Chalo. Vijaya, why are you not answering? Why Vijaya is not answering? Chalo, let us come to the last concept of today. Uniform thermal conductivity. Uniform thermal conductivity. So look, I have already told you in the last class that temperature changes with, conductivity changes with temperature. Okay. What did I tell you? That conductivity is a function of temperature, right? Yesterday we talked about this, no? Do you remember? Conductivity is a function of temperature. So if temperature is changing, conductivity changes. So in solids, if temperature increases, conductivity decreases. In liquid, if temperature increases, conductivity decreases. In gases, if temperature increases, conductivity, what happens in gases? Conductivity increases or decreases? Increases. Very nice, very nice. So that is why I was saying that you need to revise. So every time when we come to that topic again, so you will get your revision. Okay. Otherwise, if you do not remember what we talked about yesterday, then you will be confused again. Arey yaar, when did we talk about this? Okay. So if you have revised, then this is your second revision. Now it has, how do you say that? It has encrypted on your mind. Encrypted is the right word, I think. Chalo, theek hai. So if conductivity is a function of temperature, but if the variation of thermal conductivity with temperature is not significant, if it is not significant, then what can we do? We can assume it as independent of temperature. We assume that it is not a function of temperature. It is our assumption. We assume conductivity changes with temperature. Of course it changes, but if the change is not significant, then we can assume that it is independent of temperature. Then in that case, what we do? So whenever we apply Fourier's law of conduction, so what is it? Q dot is equals to minus Ka dt by dx. For example, x ले लो. First case ले लो rectangular का, ठीक है? Now, because K is independent of temperature, so whenever we integrate, so dx is equals to minus K a dt. So whenever we integrate, we do not need K inside. Yes, if it is a function of temperature, we need to put it inside integration. But because k is independent of temperature, we can take k outside, and our calculation simply gives you Ka T1 minus T2 by L, that we have done earlier. So there we assume that the thermal conductivity is constant. So it was that case. That was a simple case. Okay, this is what we have already done. This is what we have already done. But let us assume that the temperature, that the conductivity is varying with temperature, and the change is significant. So you cannot take conductivity as constant. Okay. So in the question, they will give you a relationship. For example, they will say that conductivity is a function of temperature, of course. Okay. And the conductivity is varying with temperature according to this relation, So now you cannot take the conductivity outside the integration. Now what do I need? Dx is equals to minus a integration kt dt. Okay, so this is, let me put here x1 to x2. So this is x2 minus x1 is equals to minus a k naught 1 plus beta t. Okay, t1 to t2 and dt. Okay, and we know that in rectangular case this is equals to 0. So I can say k dot x into L is equals to minus a. Now this k naught is a constant. Not the conductivity is constant. This is a separate constant. It can be anything. It is not k. It can be any constant. Okay, and beta we will see what is it, and it is temperature. So conductivity is a function of temperature. Okay, so I can take k naught outside. And integration 1 plus beta t dt. T1 to T2. So now can I write it as minus k naught a by L. Let me not write L here because I will, leave it there only. Okay, now when I do the integration, I will find t plus beta t square by 2 t1 to t2. Now, so now q dot x is minus k naught a by L. Now I can apply the boundary limits t1. Okay, is it clear? Now because minus is there, because minus is outside, so can I take q dot x? I'll take q k naught a by L t1 minus t2 plus beta by 2 t1 square minus t2 square. Now every time you do not have to use this equation. What I am saying is, if the relation is this relation can be anything. Thermal conductivity can vary with temperature by any relationship. That relationship will be given in question. So you will take it inside and you will integrate accordingly. But mostly this relationship will be given to you. So you can use directly this equation. If this equation is not given, then you cannot use this equation. Is it clear? But you need to take it inside the integration and you need to integrate it with the dt. Okay? Is it clear to everyone? Okay, chalo. So what is beta? Beta is, so if let's say this is your rectangular ball of thickness L. Okay. And here it is T1, here it is T2. So KT is varying with thermal conductivity is varying with temperature by this relationship. So what is beta giving you? Beta is giving you the slope of this temperature gradient line. Okay. So this slope of this temperature gradient line, it is giving you the slope of beta gives you the slope of temperature variation. How the temperature is varying? Is it varying linearly? it is varying hyperbolically, or how it is varying. Okay, so now let's say if beta is equal to 0, if you put this equal to 0, then thermal conductivity is equal to k naught, which is a constant. So that means it is a case of uniform thermal conductivity. Now it is independent of temperature, uniform thermal conductivity. And it shows that you can draw a linear line if it is uniform thermal conductivity. Linear line. Although tomorrow we are going to prove why we draw a linear line. Okay, you see this is a linear line. So tomorrow we are going to prove this, why temperature is linearly varying with X. But still, this also tells you that if the temperature is, if the conductivity is independent of temperature, then it is a linear line. It is a linear line. Okay. So if beta is greater than 0, if it is greater than 0, then KT is positive. Okay. So it is varying like this. It is varying. So beta is a positive slope. Beta is positive. It is positive. Okay. And if the thermal conductivity is varying negatively with X. Okay. So this is beta is less than 0. Then you will see this kind of curve. Okay. Okay. Yeah, what K increases along L. If beta is greater than this 0, K increases along L now. You see what is happening here. If look, K naught 1 plus beta T. Okay. So it is about K and temperature. Okay. So if look, temperature is decreasing, right? In this direction along L. What is happening? Temperature is decreasing, right? And beta is positive. So beta, this is positive, this is negative. Okay. So the combination of them will tell you if conductivity is increasing in X direction, in L direction, or X direction, whatever you want to call it. Okay. So it is not necessary that if beta is greater than 0, then K increases along L. It is not necessary. The combination of them will tell you what is the value of beta and how much temperature is decreasing. Okay. This is a little confusing, yes, but you don't worry about it. Okay, it's not very frequently asked anyway, but it is a little confusing. Okay. Okay, I'll tell you one more thing. 99% you will always assume in question, it is given in question that uniform thermal conductivity. That means thermal conductivity is not a function of temperature. Only 1% you can get a question that there is conductivity is a function of temperature. Okay, only 1% chances are there. 99% of the cases you are going to use uniform thermal conductivity. Okay. Okay. Is it clear? Let us see this question. Tell me very quickly what is the right answer. So they are saying one-dimensional steady state heat conduction without heat generation in a plane wall with boundary conditions as shown in the figure. Okay. So it is saying T2 is greater than T1. That means this is the direction of heat transfer. By T2 is greater, like this. T2 is T1. Okay. And the direction of X is like this. Okay. So at X is equals to X1, T is equals to T1, at X is equals to X2, T is equals to T2. Okay. Now tell me. Here it's saying the conductivity of the wall is given as like this. Okay. So K is equals to K naught plus beta T. Beta T. Okay, it is given. This is K is equals to K naught plus beta T. Now K naught and B are positive constant. Okay, so they are saying this is positive and it is saying this is also positive. Okay, now you see one thing, that as X is increasing, that means you are going in this direction as X is increasing. So temperature is increasing or decreasing? Temperature is increasing or decreasing? Yes, increasing. Okay, so as X increases, temperature increases. So I can say K also increases, isn't it? Because bhaiya, this is positive, and then temperature is also increasing, that is positive. So K is going to increase as temperature is increasing. Okay, now so that means K is positive, and I know that Qx is equals to minus Ka dt by dx. Okay, so K is positive, area will be positive. Of course, we know that area cannot be negative. So that means dt, temperature gradient, dt by dx is negative. That means as X is increasing, temperature gradient is going to decrease. Temperature gradient is going to decrease. Negative means what? You will get a negative value. That means it is decreasing. Okay. Why increase? Why everyone is saying increase? Why? Are you able to understand this? It's a simple thing. No, everything is, look. They are saying, what are they saying? They are saying that conductivity is varying like this, and this term is positive. This term beta is also positive. Okay, because I don't know if beta can be positive or beta can be negative. Beta can be positive, beta can be negative, but in the question they have given it is positive. Okay, now based on the value of beta, K will vary. Okay, but because beta is positive and K is also positive, that is in the question they have given me. Okay, beta and B are positive value. Now, so as they are asking, as X is increasing, the temperature gradient, what will happen with temperature gradient? What will happen with, is it going to increase, decrease, or it will remain constant or be zero? Okay, so I know this is the relation. Ka dt by dx. Now I already know that area will be positive, of course. Area cannot be negative. So if K comes out to be negative and this comes out to be negative, that means we have a positive value. Okay, so in order to justify this minus, there can be at least one minus. Okay, agar yahan pe ek minus hai, if there is one minus here, that means at least there could be one minus. Okay, either K will be negative और dt by dx will be negative, because अगर दोनों either कोई भी एक, एनी वन, बिकॉज अगर दोनों नेगेटिव हो गए तो ये वैल्यू फिर पॉजिटिव हो जाएगी. ओके, तो लेट मी रिमूव एवरीथिंग सो दैट ये सब घिचपिच जो है. ओके, माइनस के ए डी टी बाई डी एक्स. अब I can find out that k is a positive quantity. Why? Because this is the relationship that they have given. This is positive, this is positive. And I can say that if X is increasing, you see, in this direction, they have given us that T2 is greater than T1. T2 is greater than T1. So as X is increasing in this direction, temperature is increasing. So that means temperature is increasing. So it is a positive value. So that means it can never be negative. No, K will be positive, of course. So K is a positive value. So now this is positive. It can never be negative. Area cannot be negative. The only term that can be negative is this. And that is what I have written. And negative means what? As X is, because it is temperature by x value. So as x is increasing, temperature gradient is decreasing. Temperature gradient is decreasing. Okay, is it clear? Okay, chalo. So anyway, we have finished in 1 hour 25 minutes. Let us give you a summary. Let us give you a summary. We started with conduction equation. Conduction. Okay, let me. We have defined heat transfer equations. Heat transfer equations in slab, plain slab, plain and composite slab. Okay, so Q equation, my Ka T1 minus T2 by L. And we have also determined the concept of resistance in plain slab, which is equals to R of slab is equals to L upon Ka. Okay. So this is what we have talked about. Then we have talked about plain or single and composite cylinders. So what happens? Q is equals to, yes, this will be positive, right? Q is equals to what? 2 pi KL T1 minus T2 upon ln R2 by R1. And we have also defined resistance in this case is equals to ln R2 by R1 2 pi KL. We have also defined critical thickness of insulation K insulation upon H naught. Then we have talked about plain and composite sphere. Okay, Q is equals to 4 pi K R1 R2 T1 minus T2 ln, one second, not ln, R2 minus R1. R2 minus R1. Okay, and we have again introduced the concept of resistance here. Resistance is how much? R2 minus R1 4 pi K R1 R2, and critical radius of sphere, this is for cylinder, is equals to 2K of insulation upon H naught. This is what we have talked about today. Then what else we have talked about? Tell me very quickly. What else we have talked about? What overall heat transfer coefficient? Overall heat transfer coefficient. What else? What else? UA is equals to 1 upon R total. Then we have talked about combination, series, parallel, and combined connections. We have talked about last topic, uniform and variable thermal conductivity. So we have covered mostly all the most important topics that are required, and at least one question you will get from there here. At least one question. Yes, I think we have covered everything. Okay, chalo. Okay, so this is what we have covered. Anything else? Can you remember? Is anything else left in this? Yes, slides you will get. No, slides you will get. You can see that in the recording section. No, yesterday's one is there. If you want, you tell me one thing. Okay, I'll do one thing. I'll share it in the WhatsApp group. Okay, the slides I'll share in the WhatsApp group. Okay, the presentation for today and yesterday I'll share in the WhatsApp group. Is that okay? You are there in the WhatsApp group, right? Okay, then I'll share yesterday's and today's presentation in the WhatsApp group. ठीक है, चलो. तो फिर I don't know when our next class is. I'll communicate you in the WhatsApp group only because I don't know the schedule. But I think sometime in the next week I will have your class, and then Saturday Sunday will be there. Can you tell me usually when do you have your class during the weekday? Is it any particular day, or sir you are not able?
Sir, hello.
No, I cannot hear you. Are you saying something?
Yeah, I have a doubt.
Okay, just wait. Just wait. Yes, tell me now. Tell me. Hello?
Sir, in that variable thermal conductivity case, I have a doubt regarding it.
Tell me.
Basically, the temperature was a function of x coordinates, no, sir. Dimension.
Temperature was a function of what?
Space.
The temperature. What do you mean by that? I don't understand.
Means dt by dx, sir. I'm asking temperature was a function of space.
Temperature, yeah, temperature is changing as x is changing. Yes, temperature is decreasing or increasing based on the higher temperature and lower temperature. Yes.
And k is a function of temperature, means it indirectly the function of the x only, no, sir.
K will be a function of x, of course.
Means in this case, if the temperature was changing continuously, the k will be non-uniform and unsteady also, no, sir. It's something like unsteady and non-uniform.
No. Yeah, unsteady and non-uniform is basically with respect to space. If it is non-uniform, steady we say with respect to time. Unsteady is that non-uniform is with respect to space. Okay, so it is a case of non-uniform.
Okay.
It is a case of non-uniform, not unsteady.
Okay.
It is still steady, but it is non-uniform.
Okay. How it varies with the x, and we need to. How can we know, sir?
No, again, how will you know is basically the relationship will be given in question. Okay, with temperature, how it is varying, and then you can, what can you do? Like, that is what we are doing, no? dt by dx. This is telling you how temperature is varying with x, and dt will be a function of your k will depend on your temperature. So when you do the integration, you will find out that. And if thermal conductivity is also varying with x, maybe there will be a variable x here as well. Okay. But the relationship, whatever the relationship will be there, will be given you in question. You don't need to worry about how conductivity is varying with temperature or space. Is it clear? Hello?
Yes, sir.
Okay. So during weekdays, timings are from 8:50. No, any day is specified or not? Like between Monday to Friday, is any day specified, or any day can happen? I mean, the class can happen any day. Is there a particular day on which the class happens? Timetable will be available on Monday or Tuesday. Okay, ठीक है. So okay. Anyway, let's not worry about that. What will we do? Whatever day the class will be, I'll share it on the WhatsApp group. I'll share the PPTs in the WhatsApp group today. Okay, and please revise what we have done today. It's very, very, very important that you revise. Okay, and all the formulas you write on a separate piece of paper. You try to solve as many questions as possible. See if you are able to solve the questions or not. And especially for rectangular slabs and cylinders, you will get questions because I mean, sphere, very few questions are asked. If you see the previous year GATE questions on the sphere, very few questions have been asked. But the rectangular slab and this cylinder, it's very important. Every alternate year you will get questions from this. Every alternate year. Okay. Chalo, theek hai. I have taken a lot of time. 35 minutes extra I have taken. ठीक है. So let us meet in the next class, whatever it is. I don't know. I'll whenever I get the schedule, I'll update you on the WhatsApp. Okay. Chalo. Please revise. It's very important that you revise. Okay. Thank you so much. I am going to okay, I'm going to
You are currently the only person in this conference.